Yeah, thanks for the organizer to invite me. So my name is Wang. So I'm assistant scientist at Robotics Institute of Mellon University. So today I'm going to talk about the data sets and the models we developed over the past few years, trying to push the limit of VSLAM in challenging environments. So in our lab, we are more focused on the corner cases in the real-world deployment. We care more about run our robot in unstructured environment under adverse world conditions. Yeah, I think we all witnessed that the VSLAM and the other SLAM has very reliable, good performance in nice conditions, structured environment. But really, what we need to do is to solve those corner cases that even happen in the structured environments. So this is just like one example of our recent model. We developed this VSLAM model, which I go a little bit detail later, that can run reliably in all kinds of challenging environments. For example, this changing illumination and with dynamic objects, with aggressive camera motion, as well as these low texture and very aggressive motion scenarios. So our recipe of achieving this robust VSLAM is to build large-scale diverse data sets for data-driven models. And also we utilize 3D geometry principles in all our model design. So first I'm going to introduce data sets we've been developing. So we released the Tartanair like 4 years ago. Recently we just released this second version of Tartanair. So we expand this data set to more scenes, more modalities, and also adding more challenging scenarios like weather, like different seasonal change, dynamic objects, and so on. You can see it really, we will also include different camera models, including fisheye and panorama camera models. This is just released. Alongside with this, we also released a ground version of this environment, collecting in similar scenes, but with different motion patterns. So Tartanair is more like an area robot. We hasn't really imposed any specific robot models so that it can be less biased and more generalizable to different platforms. But with Tartan ground, we are focusing on ground vehicles, but we also keep in mind we want less bias. So we randomize the height, the noise, so that it's not tied to any specific ground robot. So these can also be downloaded from our website. So these are Tartanair, Tartan ground are collecting large-scale simulation environments. In Air Lab, we also released this real-world data set for multimodal SLAM. So these data come from our field test in the past few years. We have diverse scenes, multiple modalities. We cover also multiple types of robots. So these data sets have been used in a couple of SLAM challenges in some workshops. So this is another off-road driving data set. It's not specifically targeting SLAM problem, but it also includes a lot of interesting scenarios for SLAM. Because we have this very fast-moving robot in these challenging terrains. So it has a lot of vibration and it has like motion blur and so on. So it creates very interesting scenarios for evaluating SLAM problems. Maybe I should reshare the screen so that, yeah, I forgot to check the video. Share optimize video. So yeah, take another deep look at Tartanair V2. So comparing to Tartanair, we have more scenes, yeah, significantly larger amount of data and in diverse environments. So these are the 10 modalities we include in this version. Yeah, it really beyond the visual SLAM and even beyond the SLAM. So our goal is to make general perception data set that allow researchers to develop different algorithms. Yeah, I think a very interesting feature we added to this version is so we allow user to customize their own data set. So we basically collect stereo images and covering all 360 degree of the view. So we you can see here it's like six images covering all 6 directions. And with this setup, we can basically customize our own camera model. Right? So this is just an example. You can sample arbitrary like fisheye images, different pinhole images. Yeah, we also we will provide all the tools released with this data set allow you to sample, easily define a camera model and sample arbitrary images. Yeah, and it is extremely easy to use. You can just pipe install, and it comes with downloading tools, the customization tools, and evaluation tools as well. So next I'm going to share a little bit about the effort of Visual SLAM, like in our lab, that trying to develop robust SLAM that work for all kinds of challenging scenarios. So just to revisit the basic 3D geometry principles, we need to find feature correspondence between consecutive frames. And based on this feature correspondence and the camera intrinsics, we can optimize our camera pose. Right? This is like a basic, very simple 3D geometry principle. So the key assumption is the feature correspondence should be perfect so that we can correctly recover the camera pose. And the matched feature are static. So you can see based on this idea, we developed the first like learning-based visual odometry model, like end-to-end model that can train purely in simulation and test on real-world data set in like all kinds of with all kinds of camera models. So this is Tartanair we developed 4 years ago. Yeah, basically it consists of matching network and the post network. First, find the dense correspondence, then we use a post network to regress the translation and rotation of the camera. Yeah, to incorporate the camera intrinsics, we designed these intrinsics layers. Basically, it encodes the focal length and optical centers of the camera model so that we can utilize a model on like real world cameras. Yeah, so for the dynamics object, we know there's we want so the 3D geometry doesn't work for dynamic scene, but if we can mask out the dynamic objects, so we can like utilize the static features in the environment so that the 3D geometry still holds. So we developed this parallel pipeline that we mask out, we detect the dynamic object in the scene. At the same time, we also regress the camera motion based on the static part of the scene. By doing this iteratively, we can mask. We can correctly mask out the dynamic objects as well as improve the accuracy of the model. So this is published in 2022, and it's called Titan-VO. So it works. It's also trained purely in simulation, but it turns out it can work in the dynamic environments like this. We just took a random walk on campus with people walking around, and we show comparing to other models or Titan-VO, it can be more robust to all kinds of dynamic scenes. Yeah, I want to quickly introduce our next work. Like predicting this assumption, right? Like if your feature correspondence is perfect, it's very easy to get a perfect camera model. So the next work I'm going to introduce is MacView. So it's awarded by ICRA 2025, the best paper and the best perception paper. The idea behind it is very simple, right? As long as we can find out which correspondence is reliable, is perfect, we can request the camera pose or optimize the camera pose very accurately. And so we still use a dense correspondence flow network as the front end. So the main key difference is that we train a covariance estimation model to model the uncertainty of the matching result. This is also trained on Tartanair. So basically, you can see on the bottom side, we have 2 images, and we estimate the flow. With this covariance estimation, we can basically understand like, which pixel is more reliable. Then based on this covariance model, we can do a filter on the feature and pick out those most reliable features. So due to lack of time, I'll skip the details of the algorithm. So basically, this gives us the performance shown at the beginning of this talk. It can basically run reliably in all kinds of environments and be robust to different challenges. Also, we did a lot of optimization of the algorithm so it can run efficiently on edge devices. So this is showing the MacView run 6 FPS on the Orin HX. So we took this payload to the ICRA and just walk around. It can just reconstruct the scene on the edge device very reliably. Yeah. So I use 1-2 more minutes introduce latest work. So we focus on build more accurate, reliable matching network to solve this correspondence problem. And so the key message here is to develop a simple end-to-end transformer-based model that unify the optical flow problem and the white baseline sparse matching problem. So these 2 problems are usually tackled separately, but we show that by combining these 2 matching problems, using one big transformer model, we can achieve better performance and also do more reliable matching with arbitrary images. So I skipped the details. I want to show like the result is really very, very reliable. So the visualization you see here is the input is the third-person view on this pinhole-like image and a first-person view fisheye image. So this visualization we show here is basically what we build upon our matching result. We warp this fisheye image to this view. So you can see it capture reliably like what's the overlap co-visible pixels, and it can basically understand. It's purely 2D, but you can see it has a strong sense of 3D. And these are just some more examples. You can see how the correspondence, how we can match image from very big viewpoint changes, and also it can with large distance viewpoint changes. So you can try it out on our with our interaction demo online. This is just a random images took from our office. Here. So these are the main collaborators, students done all these amazing works. Thanks a lot. Happy to take questions.